Welcome to our AP Chemistry Chapter 10 notes. It's equilibrium or general equilibrium that we're going to be discussing. To illustrate general equilibrium, I want to discuss a scenario. So I present to you how my son and I play. So I get home and I'm like, hey son, there's a big pile of blocks. Let's build some towers. And my son, who we have nicknamed Destro, of course, as any young child would do, doesn't build towers, he destroys the towers. So he knocks the towers back to a pile of blocks. And because we like to play this for more than 2 minutes, I keep building towers, and he keeps knocking them down. And what would happen if I got so good at building towers that I could build the towers up as fast as he could knock them down? So imagine he and I are kind of like on the floor with our pile of blocks, maybe going around sort of a circle, and I would build a tower, and then I'd move over to the left, and I'd build another tower, move to the left, build another tower, and he's coming in from the right, knocking down a tower, moving to the left, knocking down a tower, moving to the left. If I was building at the same rate that he was destroying, would there be any actual change in the number of towers that are standing up at any point in time? Hopefully the answer is no. If I have 4 towers up, then every time I build a 5th tower, he would knock down the first tower, and I would still have 4 up. Because the number of towers remains the same then when we're working at the same rates, does that mean we are done with our motions? Are we done with our, if you will, reactions? And hopefully the answer there is no again. We're still moving. I'm still building. He's still destroying. But we are rates of a motion that are opposites of each other going at the same rate. So my building and his destroying, which are opposites, go at the same rate. And so we have an illustration of equilibrium. Equilibrium is where we have opposite reactions going at the same rate. We're not done with the reaction. It hasn't stopped, but there's a forward and a reverse reaction that are opposites of each other. And when they go at the same rate, we can't tell that they are doing anything more because, like someone observing us playing, you would only see 4 towers in a given moment. So this is very much like a chemical equilibrium. In more of a chemical form, we would have a reaction like reactants A and B forming products C and D. And we'd have the reverse reaction, C and D, forming products A and B. Now to simplify this, and I'll write this all the time, when it comes to equilibrium, we use a double-sided arrow like that, showing we have a forward reaction and we have a reverse reaction, and they are going at the same time. Now, usually our arrows are more like harpoons. This is technically called a double harpoon, but we usually leave the other piece of the arrow off just to make it look a little neater, to make when you put them together so close they don't run into each other. It's not wrong if you put a full arrowhead on them. But that's our equilibrium arrow, double-sided arrow, showing that we're doing this reaction, what we'd call the forward reaction from left to right, because we all read from left to right. And then we'd have the reverse reaction that is going from right to left, because that is the reverse of the way we read. It might be best to start off now that I've kind of introduced the topic of equilibrium to you to explain what equilibrium is not. Let's get the non-examples going. Equilibrium, the equal part of equilibrium, is not. It is not. The equal part of equilibrium is not telling you you have equal amounts of products and reactants. I can have equal amounts of products and reactants and not be at equilibrium. I can be at equilibrium and not have equal parts of products and reactants. I could be at equilibrium and have equal amounts of products and reactants. That is a possibility. It is pure coincidence. There is no connection between equilibrium and the amounts of products and reactants. Equilibrium is not permanent. Just because a reaction is at an equilibrium at the moment does not mean I can't do something to change it. Now, it would take an outside force to change it, but that's easy enough to do. We have lots of ways to change equilibriums in chemistry. Part of your job in this chapter will be figuring out, if I did this kind of change, how would that change the equilibrium? So equilibriums are not permanent, and they're not instantly established. It could take a while to reach equilibrium. On the other hand, it doesn't have to. How long does it take to reach equilibrium? Well, that's not this chapter. That's actually the previous chapter of kinetics. We would do a kinetics look at how long would it take, because that's exactly what we were doing in kinetics. How long would it take to reach a particular amount of product or reactant or something like that? So this is going to be after the kinetics portion. Equilibrium is after kinetics has occurred. Now there's no net change, so kinetics is done, and now we've reached equilibrium. Equilibrium is not a stop in the reaction. The reaction is still going, but we have the forward reaction going and the reverse reaction going, and they're going at the exact same rates. That's the equal part of equilibrium, is the same rates, equal rates of forward and reverse. It doesn't look like anything's changing, but there is still chemical reactions going on, guaranteed. And when they ask that on the test, be sure you answer that way. There are some reactions that do not reach equilibrium. These are kind of like a definitional thing. By definition, there's some reactions that don't have a reverse arrow. They have a one-way arrow only, meaning they don't reach equilibrium. They just go till they run out of reactants. One of those things is like the dissociation of a strong acid. To show that hydrochloric acid would dissociate into hydrogen ion and chloride ion when placed in water is a one-way arrow. It would not be a two-way arrow because this reversed would never happen with hydrochloric acid. It is such a strong acid that it's easy enough to say 100% of the molecules of hydrogen chloride will ionize. Now, speaking of equilibrium not being permanent, equilibrium is not the same for every condition of temperature. So one of the ways to mess with equilibrium is to change the temperature. So we do such things as say, this reaction's at equilibrium at 25 degrees Celsius or something like that. We would specify the temperature. And if they don't specify the temperature, you assume standard temperature for whether you're working with gases or not gases. Okay? Tell me that's not confusing. I know. For gases, it's 0 degrees Celsius. For everything else, is 25 degrees Celsius. But the temperature is usually noted. Now, a lot of students don't understand that that's why they would tell you the temperature in the problem. They're like, they're reading an equilibrium problem, and then suddenly they get temperature, and they go, I don't know what I was supposed to do with the temperature in the equation. You're not. It's because you have to tell the temperature to let you know that the numbers you wish to use are valid. You can't look in the back of the book at a chart for 25 degrees Celsius if your reaction's occurring at 300 degrees Celsius. It's not going to match. Okay, so that's what equilibrium is not. Let's look at an actual official answer, because I want you to see how we lay out our reactions when it comes to equilibrium. This is a beautiful method in which we do our problem solving in equilibrium. It is one you really should do. Are there ways you could get around it? Yes, there's none that works so well and so beautifully and keep you on track so much as building what we call a rice table. So do you see why we call this a rice table? RICE being an acronym for reaction, initial, change, equilibrium. Now on the test, they don't often refer to the R. And I think it's because they don't want to seem like they have some sort of cultural bias. I don't know. It's like I certainly am not culturally biased, but I do like eating rice, no matter which way you make it, it seems. So whatever culture you make right, just bring it in. I'll eat it because it's awesome stuff. But anyway, they'll talk about ICE tables. They're saying the same thing, they're just not including an R for reaction. But you can never get started without a balanced reaction. So we're going to call it a rice table. Here's what's going on. We've got some reactant forming some product. Oh, check it out, equilibrium arrows. We also have some product going to form some reactant. However, initially I had some amount of that reactant. Do you see how many moles? And initially I had some amount of that reactant, and initially I had no product. Okay, so before the reaction started, if I had a magic ability to mix things but not let them react, the way we do that is just not mix them. But if I had a way to mix them and not let them react, this would be what I'm starting with. Now, do note the labels all match with moles. That's super important. You can only put moles and molarity into a rice table. You cannot put any other units. So you will need to always, you can't put in grams, won't work. So you're always going to have to change. If you're given something other than moles and molarity, you're going to always have to convert to moles or molarity, whatever is convenient. For general equilibrium, moles is great. For acid-base equilibrium, which is a couple chapters away, molarity is great. You'll get the hang of it by then. So what's occurred here? I have some reactants and zero products. Well, if I have nothing but reactants, what's the only thing that really is going to occur? The reactants are going to react to make some products. So notice how I'm minusing. I'm using up some reactant, I'm using up some reactant, and I'm gaining some product. Now let me point out, notice how my numbers are different. Okay, hopefully you've already caught why, but I'm going to use up 2 times as much of this as 1 time much of that. And I know that probably was killing grammar, and there's some English teachers rolling over in their grave right now. But 1 oxygen is 0.028, so 2 times that amount would be that. I'm also forming 2 times that amount. So that's the amount of total change that will occur before I reach equilibrium. So what do I have left at equilibrium? Well, we do the math. That minus that is that. That minus that is that. That plus that is that. And I do strongly recommend putting the minuses and pluses in the change row. It really will help you keep straight what's going on. Now, we're also told some interesting information. We're told this is a 1 liter vessel, and how do we measure molarity? Moles per liter. So we could have easily just done everything we did in molarity just like we did in moles. Truly possible to do. And again, that becomes super useful when we get to acid-base equilibrium. For right now, just know we can do moles or molarities, but that's it. No grams, no molecules, nothing else like that. Just moles and molarity can go in a rice table. Okay, so that's how a rice table works. R for reaction, I for initial, C for change, E for equilibrium. That's what a rice table is. We put in our numbers, and we can figure out what we have at equilibrium. Okay, now I have a new situation, a new scenario. So check this out. I'm starting with 0 of that, and some of that. So how is this different? I'm actually starting with what used to be the products, and I have no reactants, or at least what we used to call reactants going on. So what's the only logical thing that could occur in this reaction? I would have to lose some of this thing that I call products, and I'd have to gain some of this and gain some of that. And notice it's still a 2 to 1 to 2 ratio, because I have a 2 to 1 to 2 ratio going on there. Very important in the change row, to be sure you're using your ratio. I've often seen people pick a number like 0.212 and literally write that as a minus 0.212. Well, that didn't work. With a 2 in front, so that they can double check that they're actually using the ratio. So however that works out best for you, but it should be ratioed according to your balanced chemical equation up at the top. That's why I like the R in the rice. Put the ratios in there. It's a 2 to 1 to 2 in this case, so I have 2 to 1 to 2 ratio. I do the math and I get that. And again, it would also have worked for molarity. Okay, so with that said, suppose I want a rate law. We just did rate laws. You should be all good with the rate laws. So suppose I want a rate law. So I'm going to do a rate law for the forward reaction. Okay, so pretending the forward reaction, which was this one, reactant, reactant, assuming single step, there's our rate law. Then we go to the reverse reaction, which was this one. Now that's the reactants and that's the products because it's the reversed reaction. We literally flip them. Okay, so I have two rates, one going forward, one going reverse, and we're going to assume it's one step, and therefore it's the slow step. Therefore, the coefficients equals the order, which is all stuff you should have picked up in the kinetics section. By definition of what equilibrium is where the rate of the forward reaction equals the rate of the reverse reaction. That's a definitional thing. That is what equilibrium is. That's what's equal at equilibrium, is the rates of the forward and reverse reactions. That is the only thing equal at equilibrium. Please, 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 please don't include anything else. The rates of the forward reaction and the rates of the reverse reaction are equal at equilibrium. So, if rate forward equals rate reverse, then substituting in those things that we saw earlier get substituted in. Let's kind of group like terms. Let's group the K's, the constants. Let's group the concentrations, and we get something that looks like this. This is a little awkward, having two rate constants. So we're going to combine them together into one constant we call K. Capital K is the equilibrium constant. This is important. On the test, it would not shock me if they had a question that simply asked you what is like the lowercase k and what is the capital K. Now they're going to ask it eloquently because they're going to always write these super nice sounding questions that make it seem so difficult. They're not that difficult. But they very likely will test you at some point in time. Do you know the difference between rate constant lowercase k and equilibrium constant capital K? So be sure you know the difference. That's why I've harped on it being a lowercase k for rate constant, and that's why I'm now harping on it being a capital K for equilibrium constant. So capital K is equilibrium constant. What's that C doing there? Concentration. I don't need that C subscript. It's there for looks. But that reminds me I'm doing equilibrium constant in terms of concentrations, because I could do it in terms of pressure. I could do it, as we will learn much later in other chapters, in terms of solubility product. I could do it in terms of acid. I could do it in terms of base. You get the idea? We have all sorts of different special Ks. There's kind of like a special K for every equilibrium situation. Do you really even need to worry about what symbol to put there? Actually, no. You are safe on the test. You're probably even safer on the test just using the K with no subscript at all, knowing that all equilibriums work in the same way. Now, in which way do equilibriums constants work? So check this out. This was the products in my reaction we discussed earlier. Prove it to yourself. Flip a few pages over. Look at what the products were. That was in the products. Okay. These were the reactants of my equilibrium. And notice how they are raised to an exponent matching their coefficient because we assume a single reaction. One elementary step. So an equilibrium constant expression, dun, 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 the equilibrium constant expression should be a K equals products on top raised to the power of their coefficients, reactants on bottom raised to the power of their coefficients. That is what we call an equilibrium constant expression. Okay? And again, don't worry, if you want to put a C there for concentration, that's fine. If you're working with pressures, you can put a pressure there. How would I look at this and even know I was dealing with concentrations in the first place? Because remember, brackets, those square brackets, is our chemical shorthand for molarity. Not moles, molarity, moles per liter. Okay, so that is Kc, equilibrium constant dealing in concentration. And this much, ignoring that, this much here from here to here is, if you're asked, write an equilibrium constant expression for, that's what you're supposed to be writing. I kid you not, there have been many, many, many years where part A of an equilibrium question on the free response was, write an equilibrium constant expression for. And like, that's this. You didn't even have to substitute any numbers. You got a 1 for looking at the reaction and writing K equals concentration of and concentration of. Okay, so I know it seems easy. I hope it seems easy. It could be easy enough and yet worth a point on the test. So please, please, please understand an equilibrium constant expression. Equilibrium constant equals products raised to their coefficients divided by reactants raised to their coefficients. Okay, let's go back to case 1. Now, for me, I'd have to flip several slides back, so I'm not going to. But looking back in your notes at case 1, let's plug in those numbers we had for the E row. So not the initial row, not the change row, the E for equilibrium row. At equilibrium, here's what we had, and then we raise it to the powers, and I do the math, and I get 0.15. And that's because my sig digs is 2. Now, K is unitless, so be sure that all your numbers cancel. Let me contrast. Lowercase k had a very lowercase k, make that look very lowercase. Lowercase k had a very interesting unit. It was always time, per time, and there might be a per molarity thing going on there, either there or there, which is why they always ask, what are the units of k? Lowercase k. Capital K should never have any units. That's molarity, that's molarity, that's molarity, or that's moles, that's moles, that's moles. It all is going to cancel. If you really want to see the math behind how that cancels, I'd have to teach you fugacity. I'm not going to do that. If you want to have some fun some weekend and Google it, that's just fine. Fugacity, look up fugacity. It's the way we get those labels to cancel. I'm not going to harp on it because it's a lot of work for no big deal, because it just makes your K unitless. So there you go. So this was case 1. Let's do it for case 2. So now I plug in the numbers from case 2. Oh, what do I notice? I notice that in both cases I ended up with the same value for K. What's that tell me? That tells me the reaction, no matter what I start with, in the end will reach the same equilibrium point when the reaction is done under the same conditions. Okay, now I've said the word same. Is that why it's equilibrium? Because we reach the same point under the same conditions? No. What's equal at equilibrium is the rates of the forward and reverse reactions. But for the same reaction under the same situations, those will reach equal rates, giving us a number that is always the same. Okay, so that's the power of equilibrium constant. It gives us a number, and then we can use that to compare for like everything else that we do. We can be like, hey, is it this number? No. Okay, it's not at equilibrium. Is it this number? Yes, it is at equilibrium. Now again, I have said for the same conditions. Okay, so please catch that. Same conditions of equilibrium for the reaction. My equilibrium values are the same. Okay. This also gives us this quickie ability. For both cases, we use the forward reaction. What if we wanted to use the reverse reaction? We would get a different K, but the K in reverse is the inverse. So we could do a little math. K forward is 1 over the inverse of K reverse, and K reverse is 1 over, okay. So you get the math there. It's right there written out for you. Okay, so let's figure this out. We have a new thing. What would we write here? Okay, well, K, C equals concentration SO2 squared, concentration O2, 1, concentration SO3, 2. 1 point right there. That could very easily be a point on the test. So please, please, please write that. Just always start by writing that. Then we plug in our numbers. Which numbers do we plug in? We're going to plug in the E row, the equilibrium row. That should make sense. So I'm going to have 0.424 moles, and this is going to be moles per liter. So I'm actually going to change that to molarity, just to let you know it's not a big deal, because again, the labels cancel. As long as they're moles or molarity, you're good. 0.212 molarity to the 1, okay, divided by 0.076 molarity to the 2. Okay, so now it's that ever fun time, calculator time, yay! Okay, and that's why these are often on the free response portion of the test. You would have a calculator then if you were using the free response portion. On the multiple choice, they would give you numbers that are so much easier than 0.424 and 0.212 and 0.076. They would give you numbers that were like, 2 and 4, maybe like 0.2, 0.4, and 0.1 or something. Something you could do by hand, specifically like in your head. Anyway, so we type this into a calculator, and assuming I could type it in correctly, I got 6.67 for this value of K. Now that takes care of the first question. My second question is, what's the inverse for the reverse reaction? So 1 over 6.67 equals 0.15. What do you notice? Oh, that's the same number we got earlier for our 2Ks that we already did in the notes. Why is that? We'll check this out. I have a reaction that is the reverse of that reaction. So if you flip a reaction, if you make products reactants, you flip a K in that you make it an inverse. It used to be with Hess's law, you flip the sign. Now we're flipping the K. You need to know how this works. Memorize that. If you flip a reaction, left to right, products to reactants, then you flip the value of K. You invert it, 1 over K. All right? One other thing, if we do something like Hess's law for equilibrium, where we add up a bunch of equations, when you add up a bunch of equations to reach the equation you want for equilibrium, you're going to end up multiplying the K's. So there you go. If it takes several steps in a mechanism to reach equilibrium reaction overall, then you can just multiply all the K's. Now, I know you're used to, like with Hess's law, you're used to adding. This is different. Similar idea, but it's different. The K's multiply. So be sure you do that correctly, not adding, but you multiply them. If there is, step 1 is blah, 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 and has a K, 1, and step 2 is blah, 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 and has a K2. What is the overall? Well, we would add up the equations, and our overall K, maybe I'll write it as overall, would be K1 times K2. And if I had 3 reactions, I'd multiply by the third one too. It's multiplication, so be aware of that. Okay, this is where we're going to pause for today and let this much sink in, and we can start practicing on what is K and what is not K, and what do you know with K and what do you not know with K, and maybe even practice some rice tables. We need lots of practice this chapter because this is a huge deal for the rest of the spring. This is like 8 weeks of our year right here about equilibriums. Different uses of equilibrium for specific situations. They're all just special Ks, but it's very, very important and a super huge big topic on the test. So let's pause and do some practice, and I'll see you again next time.